So last time we finished section, what was that, 6.1 on finding areas between curves, right? And we constructed the idea based on an extension of the definition of the area under a curve, but in this case, in the situation in which we have two curves actually bounding a region, and then we found those areas. So we are going to extend that type of idea. We're going to use an integral to define not an area, but actually a volume of a solid of revolution. So what's the picture? Oh, actually, there's a couple of methods to find those volumes. Number one, which is the one that we covered, that we discussed today, is the disk washer, which is actually basically the same model, the same setup, except that the disk method comes into play when we are obtaining a fully solid region, as opposed to the washer method, which we obtain a solid with a hollow part in the middle. All right. So the picture for this is this one. So we have some function f of x, some function whatever that is, and we will rotate this graph, right? We will rotate this graph. Maybe you've seen those ornaments they sell at Party City that create solids. You put them together. They have shapes of bells, hearts, different shapes. So you can think of a solid of revolution by rotating those kinds of ornaments. But in this case, what we rotate, it's a function f of x, okay? And well, the end result is going to give us, okay, something reflected like this. But let's give this a character of a solid. Now let's make this look like a solid. Yeah, these ones are not easy to draw, but I mean, I think you get the picture of how this is really a solid of rotation. And well, so we are going to construct a formula to find the area, or rather the volume of this solid of revolution. And as an analogy, let's real quick go back to finding the area under the curve. So from the area under the curve from A to B was found initially by partitioning the region of integration into rectangles of the same width. All right. So we have a rectangle, and the idea was to get a rectangle that has a width delta x and a height y in the vertical direction, which typically is our f of x. And then, well, so what we did is find that area of the rectangle plus the area of the second rectangle plus the area of the third rectangle, etc., depending on how many rectangles did we use to find that area. But of course, recall that doing it that way was not going to give us the actual value of the area. It was just going to give us an approximation. So what we did is to make that delta x as tiny as possible, so we can have actually infinitely many of those rectangles and give us the exact area under the curve. So in a similar way, we will define the volume of a solid of revolution. However, so we can have a visual of the picture here. So what happens when you rotate a rectangle? What geometric shape is obtained?
Cylinder.
Circle, cylinder. Yes, it's a cylinder, or a disc. Well, actually, the official name of the geometric shape is a cylinder, but typically we relate cylinders to shapes that are taller than they are wider, and for cylinders that are shorter and wider, typically either we call them coins or we call them discs. You know. So that's why we call it the disk method. So in this case, we are going to partition the solid, the region that we rotate. But in this, instead of doing the whole thing in the picture, let me take that sample over here. So this is the circle that we obtained when we rotated, but we're actually not obtaining a circle but a cylinder. So let's make this look a little 3D. And this gap in between, that's going to be the thickness of the disc, or the thickness of the cylinder, or the height of the circle, which in this case it's still going to be delta x sub I. Alright, delta x sub I, because the subscript I is just to denote that we are taking the ith disc, the first disc, the second disc, the ith disc, because we're ultimately dividing this into n disc, and n can be really big. The bigger the better, infinitely many, the actual volume, right? That's the whole idea behind the calculus of obtaining this. Okay, so, and then of course a cylinder has a radius. This radius right here, it's the same radius. This radius is the same radius there, but isn't it the height of the function, which is simply f of x or y? So, but in this case, to give a more a more geometric context, what do I mean by geometric context? Let's call it radius for now. Let's call it big R of x. Okay. And then from here, well, let's start from area, then from volume, then add n of them, then infinitely of them, and then integral. So that's how we're going to go. So the area of a circle, isn't that pi r squared? All right. However, in our terms, in this context, we have an area that depends on x in this case. And that area is pi times r of x quantity squared. Okay, that's based on this picture right here. Now we're gonna go from here, from this area to the volume of that cylinder. So recall that the volume in general, it's the product between the area, the bottom area times the height. All right, and that's true for cylinders, for cubes, rectangle, rather parallel pipettes. Actually, they're called boilers, those rectangular boxes. So in general is area times height. So from here we're going to find the volume of the cylinder, which we know we have something already for the area, which is pi r of x quantity squared. But what's the height of the cylinder? It's delta x of I, right? Delta x of I. You know what? Just to be consistent with notation, let me call this also x of I. All right? So I know this height is really the length because of the perspective of the disk that we are sampling. However, well, it's still that height. Okay. So that's the volume of that disk that we sampled from the solid that we rotated about the x-axis in this case. Okay, so from here we want to find the volume from here to here, for example, whatever limits in this case. So we would get that by adding the volume of every single disk that we partition in the region. And again, in this case, we can partition that into 5 disks, but of course that's not going to give us the actual volume. 100 disks, well, maybe a little better approximation, but to get the actual result, how many disks do we need? Infinitely many, right? Infinitely many disks. So number one, the volume would be approximately the sum from I going to 1 to n pi r squared of x delta x sub I. So what is that sum representing? So the addition of the volumes from 1 to n, where n is the number of disks that we partition. But again, we have an approximation symbol, not an equal sign. If we wanted the equal sign, in order to make it equal, make that delta x as tiny as possible to allocate infinitely many disks. How do we do that? Find the limit. N approaches infinity of the sum from I going to 1 to n. And well, by definition of Riemann sum, what's the limit as n approaches infinity of the sum?
The integral.
And that's the integral. So that's the integral of from a to b pi big R squared x dx. And well, here we still have the context of the radius. We have the big R, but in general we're going to work with functions f of x, g of x, f of y, g of y. So let's just go back to the usual notation. Number one, I'm going to take the pi outside of the integral, and this will be f of x squared dx. And that's going to be our formula here to find the volume of a solid of revolution. In the same way that you define a formula to find the integral, to find the area under the curve, so here we have a construction for the volume of a solid of revolution. Alright, so how about we look at one example, well actually a few examples. So let's find the volume of a solid obtained when rotating the region, actually when rotating about the x-axis. I forgot to type that part. It's important because that matters. And bounded by y equals to the square root of x, the x-axis, and x equals to 4. So in a similar way that yesterday, that we started with a problem in which everything was given, just ready to set up the integral, we're going to do the same here to warm up with this type of problems, but still, let's sketch the region. So y equals square root of x. Graph looks like this. It's also bounded by the x-axis. Alright, and x equals to 4. 1, 2, 3, and 4. Alright. So we will rotate this region about the x-axis, and as an end result, we're going to get this solid. It's like a sideways cup, if you will, but it's actually solid. So it's really not a glass. It's like a bullet, if you will. It looks like a bullet. Okay. So let's set up the integral that calculates this volume. So volume equals to pi integral from a to b x squared of x dx. Okay, and in this case we have the limits of integration from the graph. What will be the limits? From 0 to 4. Alright, the integral from 0 to 4 square root of x quantity squared dx. Well, in this case we can cancel the square with the radical, and this integral will be really simple to compute. What's the integral of x? I mean, that's x squared over 2 from 0 to 4. The rest of the problem is basic arithmetic by using the fundamental theorem of calculus, f of upper limit minus f of lower limit. That's 4 squared over 2 minus 0 squared over 2. And well, 4 squared, which is 16 over 2, that's 8 minus 0, that's 8 times pi, 8 pi. Number 1, this is like the simplest case and the simplest way to, the simplest point of view of the problem. But of course, not all regions will be this simple. And actually, I'm going to go back to this problem to show you a different perspective, which is actually the generalized way to set up this volume problem. So let's look at a second example. So let's see what we have. Find the volume of a solid obtained when rotating the region bounded by y equals x and y equals x squared about the x-axis. And that's all we have this time. This time they're not telling us what the limits of integration are, but I think we already have some practice about that from last time. What would we do in order to find those limits? Set
the point of intersection.
Point of intersection, right, by setting the two equations equal to each other, right? So that's what we're going to do. But first, sketch the region. And what do we have? Y equals to x and y equals x squared. All right? Okay, nope. We use a different color here. And well, we will rotate again about the x-axis, and the end result will be a solid a solid that looks like this. So it's like a it's a what?
You mean that looks like cut onion?
Maybe like a cut onion piece, like a potato fry, I guess, but rotated. But it's solid on the edges. It's kind of hollow in this part, but still solid on the corner at the origin, right? So in this case, we are still using the disk method. We're not using the washer method. For the washer method, you'll see how it works. Well, in this case, when we set up the area between two curves, well, we have two functions together, an upper function and a lower function, or top minus bottom. So we are going to do the same thing for this type of problems. So volume, it's the integral from a to b times pi, and that's going to be the top squared minus bottom squared. In this case, I'm just writing the formula like this because, I mean, without actually deriving this formula, because otherwise it would have been more complicated to have two different Riemann sums. So we did it. We did the derivation with the simplest case. But now that we have the context, where it comes from, what it is, we just extend to the usual top minus bottom, and later in later examples we're going to do the rightmost minus leftmost. So, well, what's that top, what's that bottom? Typically we'll label this f of x and g of x in the same way that we label them when we found the area, top minus bottom, f minus g. So in this case, we're going to do a representative rectangle, so we can easily see the top and we can easily see the bottom one. So in this case, let's set up the integral. Volume equals pi times the integral of the top function. Which one is the top one in this case? The line or the parabola? The line. So x, quantity squared, minus the parabola squared. Oh, were we missing something? The limits, right? Otherwise, we were just going to get an antiderivative with a plus c, a family of functions, not a volume. All right? And we don't have like an initial condition to find that. No, we want a numerical value. So let's go ahead and find those limits of integration by finding the points of intersection. And we do that by setting the two equations together, solve the polynomial equation, the same way we did it last time when we were finding the limits of integration to find the volume, the area between two curves. So Same tools. X squared minus x equals to 0. Again, we don't divide both sides by x, because dividing both sides by x, that's potentially dividing by 0. And what happens when we divide by 0? You know the whole story. And if we did that, we would end up with a first degree equation, only one solution, but the picture is telling us that we should obtain two of them, so we would have those inconsistencies here. Alright, so finding the greatest common factor, zero product property tells us that x equals to 0 and x equals to 1. And well, the picture is consistent with the result, right? X equals 0 and x equals to 1. Coming back to the integral, let's write down the limits from 0 to 1. Let's simplify the integral first. 0 to 1, that's x squared minus x to the 4th. And again, this integral is really simple in the sense of the formula, the method that we carry for this. We only require the general power rule. Add 1 to the exponent, divide that by the new exponent that we obtain. So that's x cubed over 3 minus x to the 5th over 5. Evaluated from 0 to 1. Okay?
The 0 formula looks at 1.
This one? Yeah. Let's make it look like a 0. Yep. So, and this x looks weird, right? Yep. So, the rest of the problem, yes?
What happens
To the 5? Oh, yeah. The pi, not the 5. Yeah, pi, it's there. I ate it. I'm hungry and I ate the pie. Yeah, I know. So pi times 1 cubed over 3 minus 1 to the 5th over 5. So that's the evaluation at the upper limit. Minus the evaluation at the lower limit. Do we really need to write that down? How about just a big 0? Because, 0 cubed minus 0 to the 5th, it's just a big 0, right? So no need. So this will really be 1/3 minus 1/5, and combining these fractions together, that has to be 1/3 minus 1/5. After finding least common denominators, this is pi times 2 over 15, and that's our final answer. So that's another example in which we rotate still about the x-axis, but this time we have a different kind of region, not just a region under a single function like the previous one. But again, like I mentioned before, I would like to go back to the first example in which I will put into a different perspective, the perspective of the top minus bottom. So technically we have a top minus bottom here, if you will, where 0 to 4, where the top function, it's the square root of x, quantity squared. But what's the bottom function in that region?
Negative x.
Isn't y equals to 0? Yep, the horizontal line. But I mean, do we really need to write this 0 squared? Not really. Not for a region this simple. But for a region that is more elaborate like this, that's where we extend the perspective to the top minus bottom, the same way we did it for areas between two curves. Alright, so same mechanics as usual. Taller minus shorter, or top minus bottom, rightmost minus leftmost, as we will do later. Okay, so in this case, let's look at example 3. Find the volume of the solid obtained when the region bounded by y equals 2 over x, the y-axis, y equals to 1, y equals to 4, they're giving us a bunch of information here, and this is rotated not about the x-axis anymore, but this time about the y-axis. All right, number one. Picture. Y equals 2 over x. Any ideas on how the graph of that function looks like?
It will be like going from the top, very top, going all the way down toward the x-axis, but never get to it.
Exactly. Actually, it looks like it's the same as y equals 1 over x, except that the number 2, what it does is stretch or rather compresses the values, or compresses the graph, right? And this is the graph. Two tails, right? Pointing to the two different infinities in this case. Let me make this look better. All right. Well, in this case, I'm not going to plot both sides or both tails of the graph. I'm just going to plot only one, because if we observe the information in this case, that doesn't include any negative part of the function. So let's see, it's actually bounded by the y-axis. That means we only want the positive part, the one on the first quadrant. And well, in this case, well, the graph of y equals 2 over x is not going to be that different from 1 over x, just slightly smashed towards the origin. And I mean, even if it looks the same, it doesn't matter, it's fine. So it's going to be 2 over x, the y-axis, y equals to 1, which is a horizontal line, and y equals to 4, which is another horizontal line. So that's the region of rotation, and in this case, it's not about the x-axis, it's going to be about the y-axis. So the end result, in this case, is going to be a graph that looks like this. All right? It's going to look this solid. All right? Like a volcano, maybe.
Looks like a trumpet.
Yeah, like a trumpet, like an upside down funnel as well. All right, but of course this is solid, right? But I mean the shape is related to any of these shapes, right? To any of these objects. Okay, so I think from here we have all the information to set up the integral. No need to set equations together because they're telling us the lower bound and the upper bound. Well, if we did the rightmost minus leftmost, the rightmost would be the graph of x equals 1 over y, 2 over y, and the leftmost would be x equals to 0, but we don't need to write that 0 squared, so we're going to treat it like one of those simplest regions in this case. So let's, number one, define a function of y, multiply both sides by x to get xy equals to 2 and x equals 2 over y. Same function, all we do is typically just interchange the letters. So volume, which is pi integral, in this case not from a to b. In the same way that we did it for areas, when we use functions of y, we change the limits of integrations from a to b to c to d. And this will be r of y with respect to y, which in this case will be really, let's just call it f of y, right? It's still a radius and from the geometric construction, but from the function perspective is f of y. So let's just plug in what we have in here. So that will be pi times the integral from 1 to 4, and that's 2 over y quantity squared with respect to y. So let's square first and then rewrite the integral. So that's going to be the integral from 1 to 4 of 4 over y squared dy Let me take the 4 outside of the integral, multiply it with pi, and at the same time what we're going to do is write that y squared in the denominator and move it to the numerator, because we cannot integrate this while it's in the denominator. So from 1 to 4, y to the negative 2. And be careful when integrating this, because as usual, in accordance with the general power rule, add 1 to the exponent, divide by that new exponent, 4 pi y to the negative 1. That's what we get when we add 1 to negative 2, but we also divide by negative 1. Let that go from 1 to 4. Okay, so let's clean up the negative signs before applying the fundamental theorem of calculus. Let's clean up the mess. Let's turn this negative 1 in the denominator as just a negative sign in front of the whole expression. And this y to the negative 1, let's write it with positive exponents. It's easier to deal with positive exponents rather than negative exponents. Okay, so that's going to be negative 4 pi. And by the way, don't be scared about the negative sign in here, because again, let's pause a little bit here. So we're finding volumes. The signs of these results have to be positive. There's no way, there's no such thing as negative volume. That's kind of weird. So, but here you'll see what's going to happen. So that's 1 over 4 minus 1 over 1, and well, to combine these two together, 4 over 4, so we can have the same denominators to combine the fractions. What's 1/4 minus 4/4?
0.75.
Negative 3/4. And negative times a negative, that's when we get back to the positive result, okay? And the 4's cancel. 3 pi is our final answer.
Yes. So if there's ever a situation where the last number we get is negative, then we know we did it wrong?
Yes, you double check your calculations, maybe especially when it comes to integrating these functions with a negative power. It's very easy to forget about this negative in the denominator. There's a very common pitfall there, so just be aware of that. Yes?
So can we simply swap 1 and 4 up and down so that we can eliminate?
Yes, that's one of the properties of integrals. You know, like when you have the integral from a to b of f of x. This is the same as saying the integral of f of x dx. You can swap the limits as long as you change the sign in the front. That's another way to express a problem. Yep. Because, I mean, we're integrating from a to b in the positive direction, but we can integrate from b to a going backwards, but I mean, the result, just change the sign. Okay, so these first 3 examples are the ones in which we rotate the region about one of the axes, either the x-axis or the y-axis. However, problems actually get more elaborate when we in this case we rotate the region about somewhere else than the x-axis or the y-axis. So like the next example, and in fact we're not going to evaluate the integral because it's going to take a good minute to go. In fact, these are going to be exam-like questions in which you are tested on how to set up the region or the plot in the region, and then from there how to set up the integral that would calculate that volume. So in this case, yes, we may not get integrals that are impossible to integrate. It's just that the integrals would be time consuming rather than hard. And while on an exam, you're limited with time. You have 2 hours and you're being tested on other topics besides this. So that's why you typically give you will be given these questions as just a setup problem, not really calculate. Okay. Set up the integral that finds the volume of a solid obtained by rotating the region bounded by y equals x squared and y equals to 2x. But in this case, about the line y equals to -3. So it's no longer the x-axis, it's no longer the y-axis. The previous couple problems, when we rotated about the x-axis, these were the line y equals to 0, isn't it? Now we're going to do the rotation about a different axis. So, so in this case, we will graph, okay, let's still graph the functions. Y equals to 2x, y equals x squared, all right? But we're no longer, right, check this out, we're no longer doing this. Not anymore. We need to go 1, 2, 3. Let me represent the axis of rotation with this dashed line. So when we rotate this solid, on the other side of the axis of rotation, this picture has to be mirrored. And it's mirrored not only on the shape, kind of an opposite direction, but also the distance between that axis of revolution and the region. Now, how many units is the region of integration away from the axis of revolution? 3 units. Okay, I'm going to count 1, 2, 3 units on the other side, and I will think of this axis of revolution as a mirror, and we will get this, right? And this is where we no longer get a disc. This is a washer this time. Do you see the hollow part, the hollow shape that we have in the center, like you punched it or something, and it's no longer solid, fully solid? So really the solid will be in the shape of like chopped onion or potato fry, you know. That's what we're gonna get. Now here is the thing, when it comes to setting up these problems, we need to consider the 2 radii, an outermost radii and an innermost radii. Okay, so I'm gonna look at this region the following way. So from the axis of rotation, we have the diagonal line y equals to 2x to be the outermost radius, the big R, and an innermost radius, call it little r, which in this case is the parabola y equals to x squared. Okay? Now, if we didn't have this hollow shape right here, well, not yet. So this is what we want. We want the solid generated. So let me give you this picture to help you set up the problem. How do we get this shape? Okay, suppose this is fully solid all the way to here. It's also solid, and it's no longer a washer. It's actually a disc, a solid. Okay. This is the equivalent of having this solid, all right? And well, suppose this big solid right here represents maybe, what's that? Your birthday cake. Of course, you're not gonna eat the entire birthday cake. You just want this slice. So this slice is obtained by cutting the bottom part. All right, I'm going to subtract this part right here. Do you see the picture of what I'm kind of doing? All right. Okay. Well, let's further analyze every single part. So from this is the axis of revolution, y equals to -3. This is the axis of revolution, also y equals to -3. And what is this line? What is this line in this case? 2x. And this curve, x squared. Okay? So if we do again the top minus bottom for, in this case we're doing the top minus bottom for big R, the outermost radius, and we're doing the taller minus shorter, or the top minus bottom, as well for the little radius, little r, the innermost radius. All right. So, okay, using the same perspective here, big R is top minus bottom. That is in it 2x minus -3, because the top is the 2x, the bottom is the -3. 2x minus -3, and little r, the innermost region, is the innermost top, x squared minus -3. And again, the smile rule comes into play here, to x plus 3 and x squared plus 3. And these are inner radius and outer radius.
Why is that the equation symbol? Wasn't it supposed to plus 3?
Yes, plus, yeah. I don't know why I put an equal sign instead. Yeah, thank you. So we have everything ready to set up the integral. So did you see how much time does it take to set up these problems? Right? And I'm doing it in slow motion just so you can see every part of it in detail. Okay, so we're ready to do volume equals pi times the integral from a to b. That's r squared minus little r squared, which individually represent top minus bottom. With respect x. And we're missing another piece of information, the limits of integration, right? And we get these limits of integration by finding the points of intersection between the two curves, that is the line y equals to x and the curve y equals x squared. Again, x squared equals to 2x, and x squared minus 2x equals 0, x times x minus 2, and from here, zero product property tells us x equals to 0 and x equals to 2. And those points of intersection are going to be the limits of integration of our integral. And coming back to the integral, this is pi times the integral from 0 to 2 of the top, the big R quantity squared, 2x plus 3 minus x squared plus 3 with respect x. And I think I need some. Yes, I forgot that square as well. Yep, squared dx. And that's the setup of the integral. And well, check this integral. It's not that hard to evaluate, but it will be very, very time consuming. Let's briefly look at it. We would have to expand those two binomials. That's going to give 3 terms and 3 terms, and then combine like terms when there's not going to be that many, and then integrate 3 or 4 terms. I think 4 terms in this case, and then do f of b minus f of a. So for this reason, you will be asked to only set up the region of integration. But of course, if you want to take the time to evaluate these integrals, this should be 184 over 15 times pi. All right, just in case you're curious. So what are we going to do for the remaining examples? So this first example in which we have the axis of rotation not anymore the x-axis or the y-axis. On the next example, we have the same region, but we are going to have the axis of rotation this time above the region of integration. Here we have the axis of rotation below the region. In the next example, we're going to do the same region but above. So you can see how you can see the differences in setting up these integrals. And then we're going to repeat the exercises but solving the problems in having the axis of revolution to be vertical lines. But that we're going to do next time.